Welcome to Google's Introduction to Quantum Error Correction. I'm Austin Fowler. I've been working in this field for over 20 years, and it will be my pleasure to talk you through the course material. Before we get started, there's a few people that I'd like to thank. Dave, Abe, and August all helped shape this course and get it in motion. And also the production team of Jessica, Ilva, and Eggles all helped polish this final result. To overview what we hope to achieve in this course, we're going to start with an overview of quantum computer hardware. There's a diverse range of hardware out there, all very exotic, very interesting, so we'll start there and make sure you have a good grounding in what it is that people are trying to build. Moving on from there, we'll go through the theory of quantum circuits. We'll go quickly, but we will start from the beginning. So even if you've had no prior exposure to the field, I hope after a few repetitions of the material, you'll be able to follow the remainder of the course as well. Moving on from there with that grounding, we'll move on to quantum error correction, building up the basic circuits that actually achieve the detection of errors and the classical processing of what to do with that information. And layer by layer, through stabilizers, many things that you won't have heard of yet, through simulators that can handle the large scale of quantum circuits and still return results quickly. We'll talk through Stim, our state-of-the-art simulator for quantum error correction circuits, and all the way up to Crumble, which helps us manage the complexity of doing computation, manipulating the data protected by quantum error correction. So without further ado, let's begin. In this video, we'll turn our attention to what is a quantum computer. And the answer is many different things. It's still very much a research field. There are many very different technologies under investigation. And this will just be a sample of some of the major technologies in this area. The ones that we'll focus on, and I stress this is just a selection of many we could have chosen to focus on, are as follows. We're going to start the journey with annealer technology, which is actually where Google began its journey in quantum hardware, and then work our way through ion traps, neutral atoms, photonic-based quantum computing, quantum dots pursued by Intel and many others at this point in time, and last but not least, the superconducting qubit technology we focus at Google. So in the beginning, there was D-Wave, and Google was a theory effort that just used the D-Wave machine. So this is a very different way of doing quantum computing. You have qubits, but the focus is not on high coherence. It's not on well-controlled manipulations of their states. Rather, you have many couplers which each individually touch many qubits. And so it becomes a process of applying constraints to the states of those qubits and then allowing the computer to settle into states that satisfy as many of those constraints as possible. In general, it's an optimizer. The catch, however, is that there's no known way to apply error correction to this approach. So as the system gets bigger, you need lower temperatures, more control. It's not fundamentally and obviously scalable, and it remains an open question as to whether you can build a big enough computer well enough using this approach and solve things that will have an impact in the real world. Ion traps, completely different approach. You use an electromagnetic trap. So the most popular approaches these days, you have a surface on which have been patterned many electrodes. Those electrodes can trap very close to the surface individual atomic ions. And it's the internal states of the electrons on those ions that you use to do computing. You can manipulate those states with microwaves, you can manipulate with lasers. There are multiple approaches to achieving fast and high fidelity gates. But this system, being based on atomic ions, has some of the cleanest properties of any system and therefore achieves some of the very highest fidelity gates of any approach to quantum computing. The challenges are primarily speed and can you make it very big? Can you make a very high quality vacuum system with many, many, many ions manipulated with many lasers or many microwave sources and make it all work together? So these systems are typically not very large, yet typically at most a few dozen ions, and time will tell as to whether the fidelity can preserve as the scale is increased. Another approach, again atoms, but this time neutral atoms. The advantage here is you can trap these with lasers, so you don't need a physical set of hardware. You don't need all of these electromagnetic rails to trap your atoms. You can set up an egg carton-like potential well where your atoms sit in the various holes. Trapping is probabilistic, but you can then move the atoms around to fill a dense grid. And there are a number of very successful companies pursuing this technology. The ability to not need physical hardware to trap your qubits means that these systems have some of the largest qubit counts, hundreds of atoms in a trap. And some of the biggest quantum computing experiments performed to date have been done in this technology. Just like with ions, the primary challenges are speed. In addition, with this approach, in many approaches, the measurement of the information itself leads to its destruction. The atoms leave their wells, and you need to continuously load new atoms. These are the kinds of technology challenges that this approach needs to solve to scale to even bigger systems. To be a little bit more detailed, this shows the fundamental setup. You have an ultra-high vacuum cell. So that is this unit here marked UHV cell. You have a source of atoms that gets trapped randomly, and you can then compress it to a dense pack of atoms with the arrangement that you wish to have. We won't say any more about that one and move on instead to yet another approach. Again, completely different, based on light. So if you have a photonic chip, you can generate single photons probabilistically, entangle them to build a bigger quantum state probabilistically. And what the diagram on the page is intended to tell you is that if you have enough of these sources and enough way of routing the successes to bigger and bigger assemblages of states, throwing away the failures as you go, you can, at least in principle, build a system that builds a very large quantum state that can be used as the foundation for quantum computation. The challenges here, well, you need to route the photons. You need to do this quickly. So when you decide success or failure, you need to respond very quickly. And furthermore, you need to make sure that photons, which typically love to be absorbed by materials of all kinds, are not lost in such high numbers that prevents you building one of these large states. So overcoming loss and rapidly switching photons are things that this approach really needs to get under control. Yet another approach, quantum dots. Fundamentally, an arrangement of electrodes that trap single electrons. You use the states of your electron to represent the states of your data. Here, this is a very well-supported approach by Intel and many other labs around the world. You can see here one of the state-of-the-art chips at time of creation where 12 electrons are held in place to do computation. The challenge here is scale. So these are very, very small. So think tens to hundreds of nanometers separation between your electrons. You really need to have at least a two-dimensional array of qubits, and as yet the research devices don't support that. Without a two-dimensional array, if a single qubit fails, maybe because the qubit, being an electron, just got absorbed into the device itself, or at time of creation, the electrodes were not set out right and it's incapable of holding electron in the first place, you don't now have a small problem. You have two computers. They can't talk to each other, one. And so this is not fundamentally fault tolerant until you have a two-dimensional array and a single dropout can be worked around. Last but not least is superconducting qubits. So here you take a regular silicon wafer and you pattern electrical circuits. A good analogy is to think of these circuits as a guitar string, a tunable frequency resonator. You can imagine that if the guitar string is not moving, that's 0. If you pluck it, that's 1. Just like a guitar string, however, there are more states. If you've ever played music, there are harmonics. So you can make the guitar string vibrate twice as fast as normal. That would be a 2-state. And just like there are higher harmonics on a guitar string, so too with our superconducting electrical resonators, we have higher states that we need to deal with. And so dealing with those is one of the big challenges with our hardware, preventing our ground state, our 0, and our first excited state, our 1, becoming 2s or 3s or 4s, which are not useful for computation. Note that in contrast to many of the other approaches where we're talking about single electrons or single atoms, and those are very, very small systems indeed, these circuits are big. So the qubit center to center is about 1 millimeter. You can see these with the naked eye, and it's a great example of how quantum doesn't always mean small. It does, however, mean cold in this case. For the data to be faithfully stored for any length of time in either the 0 or 1 state. The thermal energy of the system needs to be small compared to that energy gap. And that energy gap is so small that the thermal energy needs to be reduced to the 10 millikelvin level. So we need a cryogenic fridge, we need a very well-shielded environment, and with that, you then have a tunable frequency resonator that can be manipulated with microwaves. We'll go through the kinds of things you can do to qubits in the next lecture. First, however, let's have a look at a few more challenges to realize this technology. They don't always work. Right? When you build a superconducting circuit, there are breaks in the circuit, Josephson junctions, whose thickness very sensitively determines the resistance and properties of the circuit. So if this is not very carefully controlled, some of the qubits will not work in the way they were designed. So you can see on the right a picture of a real device and actual error rates of that device. And you also see some of them are missing. Some of the qubits that should be there are not. These are qubits and couplers that were determined after manufacture to simply not work well enough to be included in the computer itself. Increasing the yield, going to larger sizes, getting that chip designed in such a way that the data lasts longer, enabling higher fidelity gates, are the things we focus most of our effort on in our Google Labs. Let's zoom out a little bit. That's the chip, but that is, again, certainly not a quantum computer. A quantum computer is everything: the fridge, the wiring, the microwave electronics, which you can see here in a rack, that drive the signals that change the states of those qubits. So just keep in mind that that is a pretty common statement for all of the technologies that we've viewed here. Quantum is not small. It typically requires a very large set of apparatus to make the whole thing work. And what we really focus on, the states, that's a tiny fraction of the entire setup. But it's the states that we will spend the vast majority of this course talking about, and that's where we'll turn our attention in the next lecture. In this video, we're going to abstract away all of the hardware details and focus just on quantum states. The zeros and ones of quantum computing, how we can manipulate what their properties are. What are the rules? To kick off the discussion, we're going to just very briefly talk about the classical case. So in a classical computer, the regular computers we're all very familiar with, you have bits, bit strings, typically 32 bits, 64 bits, and we manipulate those. And again, in the classical world, we don't think about the physical implementation. There'll be nothing in this lecture about the quantum physical side of the implementation. We just focus on the rules of manipulation. And we know we can do certain things. We can take two registers and we can add them. We can multiply them. We can do logic operations on them. We can bit shift them. And in a typical processor, there will be literally hundreds, not thousands, but hundreds of different things that you can do to the data. Those are the rules of manipulation. In practice, we don't typically write code in assembly anymore. We have higher level languages, and there is a very direct analog of all of that in the quantum case. We'll start with the very, very basic operations, manipulating bits, small collections of bits. And little by little as we go along, we'll start talking about how you do larger scale operations. So let's begin. What can you store in a quantum computer? It's not just a string of bits anymore. If you have a collection of quantum bits, collection of qubits, what you're allowed to store in that, or what's possible to store in that, is a set of complex numbers, one for every possible state of that system. So if I have 3 qubits, 8 possible states, you can store 8 complex numbers. If I was to represent the state of the quantum computer in a regular computer, I would need an array with length 8, one space for each complex number that can be represented. And it's really worth pausing here and thinking about what that means physically and accepting the fact that no one really knows. How is it possible that a small amount of hardware can store an exponentially large amount of information? where does that live? How do all of those different numbers physically manifest themselves in the universe? And I would say no one really knows. Nevertheless, we can verify experimentally that this is indeed possible. You can, in fact, one by one, change the amplitudes of each of those states to store all of this information, and you can manipulate it. So this is what can be in a quantum computer with just one extra condition. Each one of those amplitudes means something. Its modulus square is the probability of observing the computer in that state. And those probabilities should sum up to 1. The computer has to be in some state, so hence that condition. Other than that, each amplitude is an arbitrary complex number, provided that condition is satisfied. Now let's have a look about how we're going to manipulate those amplitudes and probabilities with gates. The first gate that we want to focus on is the bit flip gate, so an X gate. Notationally, when it's given a state 0, it produces the state 1. When you give it the state 1, it produces the state 0. Of more interest is what happens when you give it a more complicated state. For example, some complex number alpha, amplitude of the state all zeros, plus some complex number beta, amplitude of the state all ones. If we use the X2 gate, the gate that is applied to qubit 2, and if we use the numbering convention that the rightmost qubit is qubit 0 and the numbers increase to the left, then that X2 gate will flip the leftmost bit. And the result is shown. You end up with alpha 100 plus beta 011. And again, it's healthy to pause here and just think what we've done. This could have been an exponentially large superposition of different complex numbers, and we have just shuffled them all around with the application of a single bit. While this is a very simple example, it gives you some feeling for where the power of quantum computing comes from. The ability to manipulate an exponentially large amount of information with simple basic operations. Looking through the remaining two, the X1 gate, qubit 1 gets flipped, the middle qubit in this case, you can see the result on the right. And finally with an X0, we are using the notation where that is the rightmost qubit. Unfortunately, being a research field, the notation is not consistent, but in this course, we will be consistent with this notation, and you would get the state alpha 001 plus beta 110. You can do a lot more than just bit flips in a quantum computer. Since we have amplitudes, complex amplitudes that can have a sign, we can also change that sign. So this is a phase flip, a Z gate. The Z gate applied to the state 0 does nothing. The Z gate applied to the state 1 inverts the sign of the amplitude. It makes it negative. And again, you can see this in action on the same set of states we looked at on the previous slide. Z2 will flip the first qubit, meaning the one on the left. However, mechanically, that means the state alpha 000 is unchanged because it has a 0 odd qubit 2. And on the state 111, where we have a 1, we have a negative sign appearing. Interestingly here, it doesn't actually matter which qubit we apply the gate to. Because the states are all zeros plus all ones in all positions, any one of Z2, Z1, or Z0 will just flip the sign of beta, doing exactly the same thing in a completely physically indistinguishable manner. Now, when we have many gates and a state at input, the standard way of representing that is with a quantum circuit. This should be thought of as music. You have a line for each qubit, time runs from left to right, and as time runs from left to right, you encounter gates that are then applied to the state. So let's trace through the action of this circuit. In the beginning, we have the state alpha, all zeros plus beta, all ones, but then what happens when we hit that first bit flip gate, that first X gate? Well, it's going to be applied to qubit 2, within our convention is the leftmost qubit, and you'll get alpha 100 plus beta 011. Moving on to the next gate, we're going to apply a phase flip, a Z gate, to qubit 1, the middle qubit. So wherever the middle qubit has a 1, we'll get a minus sign. And you can see the result on the right. And we're not done. One more bit flip, this time qubit 0, the rightmost qubit, and that turns the input on the left to the final output, alpha 101 minus beta 010. And you could, of course, have a longer, more complex circuit, and you would just continue to apply these gates one at a time. These are just the beginning of the story, though. There are many more interesting quantum gates we wish to introduce. The next pair of them are, as shown, a Hadamard gate that takes a 0 as input and produces an equally weighted superposition of both 0 and 1. This state has the property that with 50% chance, when you measure it, you'll see either a 0 or a 1. And it's a common enough state that it has a name. It's called the plus state, and we will see that quite regularly throughout the course. On an input of 1, it produces almost the same state, just with a minus sign. And it should be stressed this is still a state with a 50-50 chance of giving you either the 0 or the 1 output. You might ask yourself, well, how is it then any different to the state up the top? How is the plus state and the minus state really any different? If you run through a second application of the H gate, you will find that a minus state goes back to being a 1 state. I encourage you to do that. Substitute the action shown on the screen into the plus state and the minus state and see that you get back to where you started. And in particular, you'll see that if you start with a minus state, you get back to 1. If you start with a plus state, you get back to 0. So these are indeed physically different states which have an observable difference after manipulation. Next, we want to actually do some more meaningful computation. To date, we've only talked about manipulating single qubits. To do anything interesting, we have to also interact qubits. And the most common gate to do that is a controlled NOT gate. If the control qubit, the top qubit, the one with the small black dot, is in the state 1, then flip the target qubit, aptly named as it's hit with a target symbol. The table of states here should illustrate that clearly. You can see that if the leftmost qubit, in this case qubit 1, is 0, nothing happens. And if it's 1, it flips the rightmost qubit, qubit 0. There's another gate that we wish to introduce, as it will be useful later, and that's a controlled Z gate. Very similar to the controlled NOT, except when the control is 1, it flips the sign of the target if the target is in state 1 as well. This makes it symmetric. It doesn't actually matter which one you call the control, and hence its circuit symbol, more like a dumbbell than anything else with 2 controls. In essence, if the state is 1, 1, the sign is flipped, and in all other cases, nothing is done. So let's test your understanding of the material so far. We've talked about quantum circuits, how it's the systematic application of the gates from left to right. Put the states shown into this, each one of them, all 4 of them, and see if you can calculate the output. Pause the video, take the time, work out those 4 answers. Hopefully you've had a chance to work that out, and what you should find, for example, for the 1-0 case, is a sequence of algebra that looks as follows. You start with applying the Hadamard gate to qubit 0, the rightmost one. Expand that out. You can rearrange the terms. You can then apply the controlled Z gate, which flips the sign of the 1-1 state. Lastly, you can then again apply the Hadamard transform to the rightmost qubit, and when you expand that out and gather the terms, you'll find the only thing left is the state 1-1. Doing this for each input will give you this set of solutions. And if you look at that, it should be familiar. That's exactly the same effect as applying a C0 gate. And this is your first circuit identity. The sequence of gates on the left, Hadamard, CZ, Hadamard, is exactly equivalent to a C0 gate. So you can interchange these gates in circuits to simplify them and manipulate them. Now we need to introduce measurement. Very critical gate in quantum computing. We'll go back to the example we had before. After the application of these first 3 gates, we had the state alpha 101 minus beta 010. Now we want to ask the question, what happens if I measure that central qubit? What happens next? Well, we'll get one of 2 possible answers. With probability mod alpha squared, we'll get the state 101. So just by measuring one of those 3 qubits, we collapse the computer state to just one of the 2 possibilities. All of the qubits are affected. Similarly, with probability mod beta squared, we'll get the state 010. So these are the two results that are consistent with measuring either a 0 or a 1 on that central qubit. Main takeaway is the state of the entire computer collapses only to those possibilities that are consistent with the measurement observed on any one qubit. For those new to quantum computing, we've covered a lot in this video. It may pay to rewatch it before moving on and thoroughly check your understanding of the algebra and how quantum circuits manipulate quantum states. Rework the examples, rework through the quantum circuits. In the next video, we're going to assume you're pretty familiar with quantum circuits, and we'll apply this knowledge and start learning about quantum error correction. In the last video, we talked about quantum circuits, and we assumed everything just worked, no errors. In the real world, that is simply not the case. It's very difficult to implement quantum circuits and get them to do what you want them to do. So we're going to spend a lecture talking about errors, all the things that can go wrong when you try to run a quantum computer. As before, we're going to start by building on our intuition with classical computers, classical errors. It's simpler. It gives us a lot to work with when we build the concepts. So we're going to start with just the classical problem of storing a bit, a 0 or a 1, and in particular, in the scenario where our hardware has errors. It has a probability per unit time of a bit flip. The question here is, well, how do we do better? If we can't accept a probability p per unit time of a bit flip, whether that unit time is a second or a century, if we want to store the data for longer than that unit time with high probability of success, what can we do? So just pause the video for a moment and think about what you could do given that type of hardware. So a natural thing to do if you have imperfect hardware is to have more of it, make copies of it. That alone is not enough. If you just have copies and they each have a probability p of failure, then after a time that scales as 1 over p, they're all going to be random and you'll still be done. You have to introduce some kind of intelligent processing for this to work. And a good example of such processing is simply taking a majority vote. If you wait for a while and a single error occurs, but we have 5 copies, as shown in this example, then by taking the majority, you'll get back to where you started. The majority is 0, reset the odd ones out, you're done. For the moment, we're going to assume that this majority processing is both instant and perfect. We will progressively remove that assumption as we go. Suppose now that 2 errors occur. Well, that's still a minority, and when we take the majority, we get back to where we started. If, however, 3 or more than half of our bits are flipped, we fail. So this is not a perfect protocol. No matter how many bits we use to increase the probability that we are successful, there'll always be some probability of failure. However, this is already pretty good. We've gone from a single bit with a probability per unit time of p of failure to just 5 copies, and now we need at least 3, so order p cubed, at least 3 errors to occur before you get a failure. In terms of terminology, what we now have is a logical bit. Our collection of 5 physical bits forms a logical bit with higher reliability than any one physical bit. We'd like to upgrade the processing even further, however, and the terminology further. So first, we want to introduce the notion of a code distance. With 5 bits, it takes 5 flips to get to the opposite state, to get from logical 0 to logical 1. That means the code distance is 5. Once we've formalized that notion, we can say that a distance decode can only fail if at least d plus 1 on 2 errors occur. In general, if I want the probability of error to be arbitrarily small, I can achieve that simply by using more and more bits, increasing the distance of the code arbitrarily, and we will suppress errors exponentially. We'd like to do a bit more with this example. We're not done with it yet. We've talked so far about taking a majority vote, which implicitly means you're going to look at each and every bit, work out what its state is, and then take a majority. This would not be a quantum compatible operation. So we're going to manipulate our processing. So we still do the same thing, but in a way that we'll be able to grow into quantum error correction, as we'll see later. So bear with me. Let's now, instead of taking the majority, look at pairwise parities. So in the first example with a single error, you'll find that we have 4 parities, the first 2 of which are 1 and the bottom 2 of which are 0. We can take that information and do anything we like with it. We choose to form a graph out of it, a 4-node graph with 5 edges, 2 of which are colored red because that's where we had our ones, our odd parity results. This then defines a graph problem. And if you solve the following problem, connect the highlighted vertices in pairs or to the nearest boundary such that the minimum number of edges are used. This is called a minimum weight perfect matching. The edge highlighted in green is that solution, a single edge that connects those 2 highlighted nodes together. That tells me which bit went bad, specifically the second from the top. And I don't actually need to go back to my data at all. I can just leave that as knowledge in my compute system. That bit is wrong. Later when I go and look at it, flip its result. More errors can then occur in the computer, and I can use my existing knowledge to calculate parities correctly. So instead of saying that the first 2 bits lead to a 1, an odd parity, we know that the second bit is wrong, and so we correct that to give a 0. That allows us to just see the endpoints of the chain of errors, that is these 2 new ones, these 2 new bit flips. Give us a new graph with 2 highlighted nodes, a new solution with 2 more green edges, and we're left finally with a belief of where errors are. We believe that the middle 3 bits are wrong. Should we then go and actually look at those bits, work out what each one is, and get the result as shown, 0, 1110, we are going to use our knowledge of errors to flip those middle bits and get back to the state we wanted. It turns out that everything we've talked about is completely equivalent to taking a majority vote. Take a moment to think about why that is. We're going to use this analogy in the quantum case, but first we need to upgrade our understanding of errors. Errors in quantum computers are much richer and much more diverse than simple bit flips. As mentioned in the hardware video, the hardware we study at Google is not really a quantum bit, a qubit. It has more than 2 levels. It's not just ground state, first excited state, there are higher excited states too. And if our system goes to these higher states, that's called leakage. And that's a problem because when we interact with a qubit that has leaked to a higher state, it corrupts everything it touches. Worse, that leakage can spread around the computer. So in this picture, we started with a single qubit in the middle of our chip that has leaked, and then just run a quantum circuit that's intended to detect errors. But what it's actually doing is spreading that error around the circuit. So this is an example of something that needs to be designed away in hardware. If we leave it to the error detection system, this is going to cause failure. The leakage will accumulate, and ultimately the computation will fail. Here's another way we can get leakage in our system from the measurement process itself. So when we measure our qubits, we use a particular microwave tone, which you can think of as being reflected slightly differently by the 2 different states, 0 and 1. It introduces a shift in the signal that is detectable back at room temperature. If you put a lot of power in principle, you get faster measurement. You also have dumped more energy into the system and you can excite it to higher states. Since we have many qubits attached to a single line, that can lead to a lot of error on a lot of different qubits. So it's something we need to manage. We want to measure quickly, but we can't do it too quick or we introduce a lot of error. Next, because our chip is sitting at 10 millikelvin, very cold, and the energy scales of our qubits are so low, energy that gets dumped is very significant. And you can see a plot of that here. This is an impact on our chip that has dumped a lot of energy, causing all of our data to heat up, become randomized, and during a period of time equal to tens of milliseconds, which works out to many hundreds of rounds of error detection. The chip essentially is non-functional, with probabilities of error close to the 50% level. This clearly, again, is something we can't cope with in software. We have to mitigate that effect in hardware. So what are we left with? We're definitely left with the conclusion that real quantum computers are not ideal. We want gates that look like this. You apply it to a state, it gives you exactly what you want at output, but in reality, that doesn't occur. We've also shown examples of types of errors that we don't even expect to be able to correct using quantum software. So how are we going to proceed? We're going to have to rely on the hardware engineers to give us a device that at least satisfies the following. We are going to assume that no matter what, Errors can happen, but they leave us in the states 0 and 1. That allows us to represent these two states as a vector with only two entries. So the case of the 0 state can be represented by 1, 0, and the case of state 1 can be represented by the vector 0, 1. If we didn't make this assumption, then we would need longer vectors to represent those higher states. And that would become problematic when it came to doing error detection and correction. So we are going to focus on this case. Similarly, when we have more than just 1 qubit, 2-qubit system, by assuming that we have no leakage to higher states, that allows us to represent that system as a vector of length 4, no more. This is very useful because when we think about the action of each gate, we can now write them as matrices. So here is our same Hadamard gate, our same CNOT gate, but this time expressed as a matrix acting on a vector. So the vector alpha beta replaces the original state alpha 0 plus beta 1. Same thing. We've chosen representation with state 0 and 1. That allows us to write it in this form. By doing so, we can now write H as the shown matrix. And the same for CNOT. By choosing to limit ourselves to just the state 0 and 1, it admits a clean form as a matrix. With that done, we can now talk about the errors which we can handle using quantum circuits themselves. So we're going to allow ourselves to have a single qubit gate, which is a 2x2 matrix, followed by an arbitrary matrix, anything at all. That's our error. Similarly, a 2-qubit gate, 4x4 matrix, followed by an arbitrary 4x4 error matrix. I want to reiterate, this is still a restriction. This is explicitly ignoring leakage and assuming those things have been handled in error. Measurement is preceded by an arbitrary error. Initialization, the state 0 in a box, is followed by an arbitrary error. We now want to discuss how do we handle only errors of this form. Well, some more definitions. These are the Pauli matrices, the identity matrix, X, Y, and Z. Very handy, we'll use them a lot. We're going to focus a lot though on just the X and Z matrices, the bit flip and phase flip matrices. These are particularly useful because we can use those as a basis for the space of arbitrary matrices. I can take an arbitrary 2x2 matrix and write it as a linear sum of just the identity gate, bit flip, phase flip, and both at the same time. And this is actually a profound small piece of math. It means that an arbitrary error really is just a combination of these simple errors, possibly nothing, maybe a bit flip, maybe a phase flip, maybe both. This means we can just focus on bit flips and phase flips when it comes to detecting errors and correcting errors, because even though they can be very complicated, these arbitrary matrices, that arbitrariness is really just a linear sum of simple things. You can also do the same for multi-qubit gates. So this is an example with a 2-qubit gate. 2-qubit error can be decomposed as a sum of 16 terms. Those terms make use of the tensor product, the definition of which is shown. You essentially take two matrices and you substitute the rightmost matrix everywhere in the leftmost. There's an example here of the identity tensored with the matrix XZ. You'll see that the matrix XZ has been substituted in the two locations where there is a 1. So we can decompose errors, and we're going to make sure that we focus on just finding bit flips and phase flips. So our goal now will be to build circuits that do this and then track these detected errors in software, something very analogous to what we did in the classical case. We'll start discussing these specific circuits in the next video. In this video, we're going to start building up the quantum circuits that we need to actually perform quantum error detection and correction in software. We've already talked about quantum circuits, the errors that can occur on the gates. Now we're going to be very explicit and build the structures to do the work we need to do. So these are some examples of things that we will need to understand well to build up the circuits that we need to do the quantum error correction work. And before we go any further, this is a great time to pause and make sure that you understand how to calculate the output of these circuits. So please do that now. We've talked about quantum circuits. make sure you understand what these things do and what the measurements will report with these inputs. So what you should have found are these outputs. And again, check your understanding if you don't, because you'll need that in the remainder of this video. So here's a useful definition. When we measure under normal circumstances, the result will be either 0 or 1. We can also define a measurement in a different basis, where we precede the measurement with a Hadamard transform, and that's called an X basis measurement. It's denoted by mx. So if you like, this is the measurement that detects whether the input is either in the plus state or the minus state. Moving on, now let's build something that's a little closer to what we actually do in the world of quantum error correction. Detection of errors over and over again. So here is a simple circuit. Doesn't protect logical states, but it's a great discussion point. So let's imagine that the top line is something that we want to preserve. It's our data qubit. And the bottom line, this is our repeatedly prepared and measured measure qubit. So what is this circuit good for? Well, in the absence of errors, it just produces the result 0 over and over again. This tells us no errors are occurring, so it's useful information. If an error does occur, well, that's going to change things. So let's have a look at how that changed things. So we have a bit flip error on our data qubit, and then when we propagate that forward, what happens? Well, it's going to flip the result of all of the future measurements. We now have a 1 state on the top qubit, and that will be reflected in the measurements. Notice that by changing all of the future measurements, the thing that really detects the presence of error is the change from a stream of zeros to a stream of ones. And this is a generic feature that we will use over and over again, that errors create changes in the stream of measurements coming out of a measure qubit. What about this? So this is not a data qubit error. This is a measure qubit error. So what will that do? Well, our data is still preserved. It hasn't been corrupted at all. We have now a measurement that is wrong. It should have been 0, but an error occurred before it and flipped it. And so that is an odd one out error. This is an example of what a measurement error will look like. So those two cases, just keep in mind, when the stream of measurements change, that's a data qubit error. When you have a single odd one out, that's a measurement error. Increasing the complexity one more step. All right. Previously, what we did was completely classical. You couldn't put any quantum state in and preserve it in any way whatsoever. Once we start using a single measure qubit to protect 2 data qubits, we can do a little bit more. For example, we can put in states of the form alpha 00 plus beta 11, and this circuit will detect whether we have states that are the same or different. And in particular, since in the absence of errors, both of these states are the same, we will still get 0 results here. It will say, yes, they're both the same in the absence of errors. This is not enough to do actual correction of anything, because we won't know which one goes wrong when an error occurs, but it's enough to take the conversation up to the next step. To go to the point where we can actually tell where the error occurs, well, we have to take that circuit and copy it more. So you'll notice this is just what we had on the previous slide, duplicated. Now we have 3 data qubits and 2 measure qubits, and this will be enough to actually locate where the errors occurred. So how? As mentioned, the thing we really care about is whether a given measurement is the same as its previous measurement or not. If it's the same, no errors detected nearby. Different, errors detected nearby. If you want to be very technical, the green circle encloses 2 measurements, and we call those a detector, because if they're the same, no errors detected. If they're different, an error has been detected. There are many detectors in this circuit. Every pair of consecutive measurements is a detector. And again, note that it's not the specific value of the individual measurements that matter. It's the parity of that set, whether that set has an even or an odd number of ones that matters. Now, let's throw in some errors and see what happens. Well, the first thing you'll notice is that now we have a detector with odd parity. And that is the definition of a detection event. When you get a parity that's not what you expected, you have a detection event and you highlight it. If we had that same bit flip in a different place, now you can see that we're getting useful information to help us locate that error. A bit flip error in this location gets detected by both of these detectors. Here you can see a bit flip error that has fired off two detection events. It starts off live here, and then it will propagate both up and down to trigger a change in the future measurement values on both of these lines. That leads to a detection event both here and here, and helps us locate that an error must have occurred on this data qubit that is shared by both. There are other locations where bit flips can occur. In this case, the bit flip occurs such that it's detected earlier on this measure qubit than it is on this one down here. So again, the pattern of detection events helps us locate where that error must have occurred. When the detection events were next to each other, we knew the error occurred in this section of the circuit. When they're aligned diagonally, we know that that error must have occurred between these two gates. So we're getting very useful information now from a circuit that's big enough to actually locate where those errors are. We even get a bit more information because this amount of time between these two gates is shorter than this amount of time here. We can say that the likelihood that we have detection events on this diagonal arrangement is lower than getting a pair of detection events aligned side by side. All of that can be used to help us work out where errors may be. So how? How does that help us? Well, we can go back, we can look at our circuit, we can look at every location where errors can occur, work out how every single possible error is detected, and add up for every possible pattern of detection events the total probability of errors leading to that. So to be explicit, this line right here, this represents every possible error, the total probability of every possible error that triggers just exactly this detection event here. And you'll notice I've shrunk the symbol a little bit just to make the graph a little bit clearer, fewer overlapping things. So this ellipse here represents the detector consisting of the measurement immediately after it and before. The thickness of the line is intended to represent the total probability, and in particular, the total probability of all errors occurring anywhere in this section of the circuit that lead to this exact detector is greater than the total probability of all errors in this part of the circuit that are going to lead to this detection event here and here, which gives this line its thinner aspect, meaning lower probability. So we can build a graph by systematically inserting every possible error everywhere in the circuit. We can build a graph of all the possible detection event outcomes with edges with thickness or probability in proportion to the total of all the errors in the underlying circuit. Now let's suppose we run an experiment and observe a particular pattern of measurement results. What are we going to do? Well, first, we're going to build all the detection events. Anywhere where you have consecutive pair of measurements that are different, that's a detection event. So let's highlight those first. Next, we want to process that. And we're going to be using minimum weight perfect matching. So we're going to search for a set of edges with the minimum weight that pair all of our detectors together or to a nearby boundary. Now, there's more than one possibility if you just count number of edges, because, for example, I could have chosen this diagonal edge here and this boundary edge down here. That still is a two-edge solution, but these edges, the ones associated with a failed measurement, and this one, the one associated with errors anywhere in this section, are more likely, so they will have lower weight and they'll be preferentially chosen, and that is just a better guess. To stress, it doesn't mean that the real underlying errors couldn't have been an error in this spot, leading to these two, and an error down here. So there is always some chance of failure. You simply maximize the chance that you've guessed correctly by choosing the most likely option. Once you've done that choice, you can sit there and say, well, based on the available evidence, I believe the errors must have been here. and then you can propagate those errors through the circuit to correct the measurements. Note that in this particular example, if we have two errors, for example, let's imagine I had an error on both this top data qubit and this middle one, that will be too much for this circuit to decode because these two errors will double flip this measurement, meaning it's undetectable, and this error down here will flip this one down the bottom. And we will think, given just a single detection event, that there must have been an error here, and we'll be wrong, and that will create a logical error. So this is an example of a distance 3 code. It can cope with, at most, the distance -1 on 2 X errors, in this case, 1 error. So if you have a sparse distribution of single errors, this code will not break. However, when we get the wrong combination of pairs of errors, this will fail. You'll guess wrong and you'll corrupt your data and the computation is over. As this code gets bigger, so as we just keep duplicating this circuit down and down and down, increasing the code distance, the number of errors that need to line up on any given path from top to bottom grows linearly. And since these errors are independent, the probability that you get at least half the locations on such a line with errors decays exponentially. So by linearly increasing the resources, you can exponentially suppress the probability of logical error. So now let's look at a slight variation of what we just studied. The same kind of circuit, but one designed to detect phase flips. So this is an example of the structures that let you put Z errors now anywhere in the circuit and detect them. For the moment, we're going to pause there, and we'll pick it up next time, combining both those circuits into the service code. In this video, we'll take a step back and talk more of the theory of quantum error correction. We need to build this up as we'll be talking ultimately about very complicated quantum circuits, and without some theoretical framework, we won't be able to cope with their complexity. So the theoretical framework we need is the framework of stabilizers, and this is what this video is about. So firstly, what is a stabilizer? Well, we start with Pauli matrices, the following 2x2 matrices: the identity, a bit flip, phase flip, and both at the same time. So this is the Y matrix, and you can get an approximation of that by multiplying the X and Z together. So we need to talk a little bit about linear algebra to have any hope of explaining this theory. We're going to be talking about tensor products of these matrices, and here is an example. If this were a 5-qubit system, all this is really saying is that we're going to flip the first qubit, do nothing to the second, phase flip the next two, and then do both on the last one. So a more compact version of that is shown here. It means the same thing. Again, if this was a 5-qubit system, we would be doing those individual operations to those individual qubits. So any signed tensor product of Pauli operators, that's the mouthful that is this slide, we'll call simply an operator. And we'll be working with those extensively. So what are some simple examples? Well, some very simple stabilizers are just individual Pauli matrices, for example, a Z matrix. So when you apply this to the zero state, nothing happens. And therefore we say the state 0 is stabilized by the stabilizer Z. This also allows you to replace the state notation with the operator notation. We'll come to that more later. A few more examples. The state 1 is stabilized by the operator minus Z. Apply that and you get back to where you started. And so on for both X, which stabilizes plus, and minus X, which stabilizes minus. Some of the terminology we need to be comfortable with is the idea of an eigenstate. So these states here are eigenstates of their associated operator. They are states that remain unchanged under application of the operator. So this suggests a substitution of notation. If an operator has a well-defined +1 eigenstate, so the state that is unchanged by its application, then instead of writing the state, we can simply write the operator. At this point, it may not seem like there's a good reason to do that. After all, writing this symbol seems just as hard as writing this symbol, but that will increasingly not be the case as we move to more complicated quantum error-corrected states. So let's step up away from single qubits to a multi-qubit state, a 3-qubit state in particular. This particular 3-qubit state is stabilized by 3 independent stabilizers. So if we flip each one of the bits, then these 3 zeros become 3 ones, these 3 ones become 3 zeros, and we're left with what we started with. So indeed, this state psi is the +1 eigenstate of XXX. And similarly, it's +1 eigenstate of ZZI and IZZ. You can and should apply these to this state and find that you get back to where you started. In this case, you may still say, well, this doesn't look much easier, this list of 3 stabilizers, but let's keep going and see where it takes us. Before we do that, let's just really work through the math here to make sure that we're all on a solid footing. So let's take one of those examples, the ZZI stabilizer, and apply it to that state. So this is the state taken from the previous slide. Here is the operator that we're applying. We distribute it across all of the states in the superposition. Z does nothing to the state zeros, and each time we apply a Z to one state, we pick up a minus sign. So there are 2 of those because we have 2 Z operators, and that again gets us back to where we started. And this is what you should have in your mind when you think about applying a stabilizer to a particular state, that sequence of steps. So how does that feed into what we're talking about, quantum error correction, in particular errors? Well, let's go back to this state, but now apply an error to it, an X2 error. We're going to go and flip the qubit 2, which in our notation means the leftmost qubit. So we now have 1, 0, 0 plus 0, 1, 1. What's changed? Let's go back and talk about the stabilizer we worked through in detail on the previous slide, but now apply it to this state with an error and see what that means. Well, previously without the error, we had the +1 eigenstate of Z2, Z1. Now, when we work that through, well, X2, you can just pull through past the Z1 operator because these are different qubits. They don't interact at all. And then X2 and Z2, which touch the same qubit, they anti-commute. Pull it through, pick up a minus sign. And what we can now say is the state X2 psi, the one with the error, is the -1 eigenstate of the operator Z2, Z1. So after suffering an error, we've changed the statement of whether we have the + or -1 eigenstate of a particular operator. So if we can work out how to measure whether we have the + or -1 eigenstate of our stabilizers, that will be a way to detect errors. And indeed, that's what we're going to do. So what circuit is capable of telling us whether a state is the + or -1 eigenstate of a particular operator? Well, the answer is this circuit. And you should go and have a go at trying to work out the output of this circuit for the 2 possible measurements, 0 and 1. Now, assuming you've had a go at doing that, let's now step through it together. So in the beginning, we're just going to have the state 0 psi, just what we had at input. After applying the Hadamard transform, that's going to give us the plus state, equal superposition of 0 and 1 on that first qubit. We're now going to do a controlled A gate, which means if the control is 1, apply the operator A to the state psi. And if it's 0, do nothing. So in the 0 case, we do nothing. In the 1 case, we're going to have an A applied to state psi. We then go and apply another Hadamard gate. So taking this state and applying that to 0, we get another plus state. Applied to 1, we get a minus state. And then if we rearrange those terms to really emphasize the 2 possible measurement outcomes, this is the measure outcome 0 will leave this state on the remainder of the qubits. If we get a measurement outcome 1, we'll be left with this state on the remainder of the qubits. And if you look at those 2 things with care, you'll see that this is the +1 eigenstate of A. A psi plus A squared psi, given A squared is the identity, is exactly what we started with. So not only does this circuit tell us whether we have the plus or minus 1 eigenstate of A on the qubits it touches, given any input state, it will project that input onto one of those two eigenstates, either the plus 1 eigenstate or the minus 1 eigenstate, depending on the observed measurement. So this is the circuit we were looking for. It tells us whether we have the plus or minus 1, and it also cleans up our state. If our state was some deviant from one of those two possibilities, after running this circuit, it will be cleaned up and only be one of those states or the other. Fundamentally, this is the circuit that keeps our forever wanting to be messed up quantum states clean. So let's now run through a specific example, locating that error with our stabilizers, continuing the example of the same state we had before, where we applied a bit flip to the second qubit, the leftmost qubit, and then that flipped our stabilizer ZZI to minus ZZI. A good exercise is now to go away and ask, well, what will the signs of the stabilizers be after these errors? And you again, take a moment, look at the states, work that out. What you'll find is that if you flip the middle bit, is that then that flips both of these signs. This is the middle qubit. If we put an error that anti-commutes with both of these Z stabilizers, both of their signs will be flipped. And last but not least, if we just flip the rightmost qubit, qubit 0, that anti-commutes only with this last stabilizer and its sign will be flipped. Let's now present one more representation of this exact same state. So we can represent psi as an explicit state. We can represent it as a list of stabilizers, and we can represent that list of stabilizers as a picture. So if we define this notation, 3 qubits, 0, 1, and 2, a shape that connects them, in this case a triangle, which is white-colored, this will be our X stabilizer. This is our X2, X1, X0 stabilizer in pictorial form. Also, we can look at the 2 Z stabilizers here, which touches qubits 2 and 1. That's this object. And finally, the third stabilizer touching qubits 1 and 0. This shape represents this piece of math. So we can also then talk about errors on this. So if we have a phase error, something that flips the first stabilizer from positive to negative, we can represent that on our diagram as a flipping of the sign of this part of the picture. This is what we wish to build on when we start discussing the surface code, and that will be the topic of the next lecture. In the previous lecture, we talked about the notation of stabilizers, how to represent a complex quantum state as a list of stabilizers. In that video, the states weren't very complicated, but as we'll see in this video, when we start to talk about the surface code, the notation of stabilizers becomes very necessary indeed. So to recap, we talked about 3 ways of representing a state: as an explicit state, as a list of stabilizers, or that same list of stabilizers but represented pictorially. We like the picture approach because that lets us present the surface code. This is the smallest non-trivial surface code, 9 data qubits in a square with an array checkerboard of X and Z stabilizers. So why do we prefer this versus any other representation? Well, let's take a look. So if we represented this as a list of stabilizers, it would already be a fairly unwieldy piece of math. If we were to represent it as a state, well, it would be even worse. This is the result of preparing your data qubits all in the 0 state and then measuring all those stabilizers to prepare the logical state. The state itself depends on the value of the measurements and is really not realistic to work with. However, it is at least good to be aware that this can be written down, and also to explicitly see how you do logical operations. So as an example, we can bit flip this vertical line of qubits. And what that will do is produce a new state that is our logical 1. Now, this is not the only way to get from logical 0 to logical 1. We, however, first, to be able to discuss those other ways, we'll simplify the notation a little bit. So our logical X operator, for the moment, is the flipping of this vertical line of qubits, but it could also just as equally well have been this line of qubits, provided it runs from the top edge to the bottom edge, and that line of X operators commutes with all of the Z stabilizers, which means it touches all of the dark squares on exactly 2 places, or an even number of places. Then that's a perfectly valid logical X operator. And this is why it's called a topological code. Many of its properties only depend on whether we connect from one place to another place, in this case from the top edge to the bottom edge, using a line of X operators, not the specific details of the shape of that line. We can do the same thing with logical Z, which turns out to be a line of physical Z operators from left to right. Here is an example touching exactly the middle row, but again, it's not the only way to do so. Once we accept that you can use arbitrary lines of operators connecting top to bottom, left to right for our logical X and logical Z, and don't really need to talk about which qubits are touched, well, then we can also drop the qubit numberings. And that's very helpful because then we can start talking about larger lattices without getting overwhelmed with the notation. We can go even further. Let's suppress even the checkerboard pattern itself and just focus on the fact that on the top we have an X boundary, somewhere that a chain of X operators can end, and at the bottom boundary the same type. And left and right we have Z boundaries, places where chains of Z operators can end. What you can now see is that given an arbitrary line from top to bottom, if we draw any line from left to right, it must cross that line an odd number of times. If we went directly, that would be a single time. If we go past and then come back and go back again, well, that's 2 more times, and always will be an additional pair of times. So it's always an odd number of crossings. You always have an odd number of locations where you have a logical Z intersecting with a logical X operator, which means they'll anti-commute, and that's something we need to be true to have valid logical X and logical Z operators. All right, so those are the stabilizers of the surface code, and we spent a bit of time talking recently about how to detect what the value of the stabilizer is. And here are those explicit circuits written down. So if you like, this circuit down here has the closest form. This is the controlled A gate we discussed earlier, where A is XXXX. These are controlled NOT or controlled X gates. This is an explicit representation of that circuit. It will tell us whether in this location we have the plus or minus 1 eigenstate of X on these 4 neighboring qubits. There is, however, a question. Okay, these circuits measure which eigenstate we have. We can use them in principle to detect errors, but what's the order of the gates? We have many possible choices. Is there a preferred choice? Before we talk about that, we need to talk about how errors propagate through circuits. So if I have a bit flip error on this top qubit, and then would like to know what does that bit flip error look like after the C0 gate? Well, we can calculate that by putting an identity operation, 2 C0 gates before it, and then just work out what this group of gates equates to, and the answer is 2 bit flips. So a bit flip propagated through the control of a C0 gate leads to 2 bit flips. Similarly, a phase flip propagated through the target of a C0 gate leads to 2 phase flips. And this is important, so we need to be careful that we don't arrange the order of our gates so that this copying process is dangerous. So let's look at this explicitly. Z errors can become pairs of errors. Bit flip errors can become pairs of bit flip errors. We don't want this to break our code. We want all of our errors to be random independent along the path of a logical operator. So for example, if we arranged our circuit such that it could turn a single error into 2 errors along this line, that would be bad. So here's an explicit example of it being bad. We've taken the example of phase flip errors. and we've built a circuit that touches these 2 qubits last. That means a single error on our measure qubit can become 2 correlated errors on our data qubits. It now only takes 2 random events to cause a chain of errors that is very close to a logical operator and will confuse our decoder, be corrected wrong. Our decoder will think, you must have had just a single error over here, and that will corrupt our data and our data will be lost. This doesn't meet the level of performance that we want. This is a distance 5 code. If you count the number of qubits from corner to corner on this square, you'll find there are 5 qubits each way. What it should take is 5 errors to go undetectably from a logical 0 to a logical 1, or at least 3 independent errors to get over halfway there and confuse the decoder so that it introduces corrections that are wrong. This is the wrong order of circuits to achieve that level of performance. Instead, it's very important that the last 2 qubits that are touched in this circuit propagate phase flip errors in a direction perpendicular to our logical operator. Previously, we saw what happened when they were parallel. You degrade the code distance. It takes fewer errors to break the code. Here, we maintain the code distance. It's still going to take a number of errors equal to, technically, the code distance plus 1 on 2, in this case 3 independent errors to break a distance 5 code, with the number growing by 1 every time we increase the code distance by 2. And that's true of both types of errors. Not just phase flips need to be oriented so their circuits propagate errors perpendicular to the logical operator. It's also true of our bit flips. So this circuit must also be arranged so that its final 2 gates touch qubits that are perpendicular. So this sets a constraint on the layout of the order of our operations so that we preserve the full strength of our carefully constructed code. Once we work with that constraint, we can find orderings that are consistent with perfect parallel application of these and still don't propagate errors badly. So here is one such example ordering, which is perfectly parallel. You'll notice that every data qubit is always touched by gates in separate time sequences. It would not be legal to have a number here corresponding to a time step that was shared. So this is a valid ordering. There is one more technical constraint that you must be able to say which one of these stabilizers is measured before any neighbor. So if you look at this one, you'll see that the 1-2 gates are earlier than the 2-4 gates. So this one is measured earlier than this one in a nearest neighbor sense. That's also an important property that you'll find is satisfied as you go around this checkerboard. It's always possible to tell a pair of neighboring stabilizers which one came first. Even though in some sense they're measured at the same time, the gate ordering gives you that ability to say that. All right, so we have a circuit that doesn't propagate errors badly, can be implemented perfectly in parallel. So now let's start doing things more than just detecting errors. How about some basic computation? What about initializing and measuring a surface code? Well, if we want to prepare the logical 0 state, we actually have already seen an example of that. You simply start by initializing all the data qubits to 0. And then once you start measuring all of the stabilizers, you'll have logical 0. Similarly, if you would like the logical plus state, just start by physically initializing each data qubit to plus. At the other end, when it comes to measurement, it's just as simple. Want to measure the qubit in the logical Z basis, meaning ask whether it's in either the logical 0 or the logical 1 state, then measure all the physical qubits in the regular way. Ask each one, are you a 0? Are you a 1? Last but not least, if you wanted to measure that logical qubit in the logical X basis, meaning is it the plus state or is it the minus state, you can do that simply by measuring each data qubit in the physical MX basis, meaning Hadamard transform and then do a regular measurement. So those are the simplest logical operations. Initialization, measurement, both in 2 possible basics. If we would like to do a bit of memory, so not just initialize and then immediately measure, but in between actually run error detection multiple rounds. We'll end up with a circuit that looks like this. This is just a slice through the surface code because it's simpler to talk about. The full circuit for the entire surface code would be too complicated to write on a slide. So let's look at this as a proxy for the surface code and check that it works the way we expect. So if we focus on the circuits that detect bit flips, the ones that measure Z stabilizers, then at the very beginning, if you want to run a full circuit, we have a single measurement that is going to tell us information about errors. Because we expect this measurement to return the result 0 in the absence of errors. The key difference between this on the slide and what we've talked about previously is this initial round of state preparation. So now we don't have to compare this measurement with the previous measurement. For a start, there is no previous measurement. We're already expecting it to be 0. So if it's 1, that's a detector all in its own right. Moving to the body of the circuit, we're back to what we've discussed earlier. We compare each measurement with the measurement before it. That's a detector. And there's one more case that's new. That's the final round of measurements. Here, we're going to compare direct physical measurement of our data with the previous measurement. These two measurements are a direct measurement of the Z stabilizer because we measure each qubit individually, and we can take the parity of these two measurements, and that will tell us whether we have the plus or minus 1 eigenstate. If they're equal, we've got the plus 1 eigenstate. If they're not equal, we've measured the minus 1 eigenstate. And that means that if we take the parity of all three of these measurements, that itself is a detector. It should be even in the absence of errors. It will be odd if there is an error nearby. So let's briefly look at a small piece of the three-dimensional circuit that is the surface code, and just really emphasize that nothing is different. It's more complicated. You would typically do this analysis in software, not on a piece of paper or in a slide, but it's not different. You still fundamentally have a circuit consisting of initialization, CNOT gates, and measurements. You have errors that propagate and trigger detection events. Fundamentally, you're going to use all of that information and you're going to build a graph that is now three-dimensional, where the diameter of the edges represents the total probability of all error processes leading to that edge, meaning detection events at the endpoints of that edge. And then when you run the actual experiment, you're going to hang those detection events on this graph, do minimum weight perfect matching on the graph to work out the most likely underlying errors that explain the observed detection events. So even for distance 5, what's shown on the page, 5 by 5 data qubits plus another 24 measure qubits, this is a 49 qubit circuit. So if we actually want to run this circuit, analyze its output, and work out how well this is going to perform, we're going to need some pretty advanced tools to do so. That will be the topic the next video. Before we close out this one, just note that if you're interested in more details about computation, we've only talked about memory in the surface code. There are a couple of references here that will take you through the details of doing CNOT gates and other more complex multi-qubit and single qubit logical operations on the surface code. But anyway, till next time, we'll get talking about our advanced tools to analyze the surface code specifically in the context of memory, where you can still learn a very great deal. In this video, we're going to start talking about Stim, which is a piece of software written by Craig Gidney that we use to simulate quantum circuits to generate output specifically for quantum error correction that we can then use to assess how well a particular protocol works. This will be an interactive presentation at points where we'll ask you to actually go to the Stim repository, download and make use of some of its getting started notebooks, and actually go in and code a few examples as we go, just to build familiarity with this tool and how to make use of it. There'll be a lot of talking about syntax and file format and kinds of things you need to do to use Stim. And with that, let's begin. So just to recall, the last lecture ended with the surface code. And the comment that even at distance 5, which is still a relatively small code, we're talking about a 49-qubit circuit. Lots of gates. How are we going to actually simulate? So the answer is Stim. You can certainly check out the original reference for that, and I encourage you to do so. But the takeaway is that this is a piece of software that lets you simulate circuits 1,000+ times faster than any other tool out there. To take an extreme example, this is distance 5 on the screen. Well, imagine the distance 100 version of that, 20 times wider and taller. Stim can simulate that circuit, 100 rounds of it, distance 100, in just 15 seconds, and then sample shots of that experiment, distance 100, 100 rounds, 1,000 times a second. So very powerful, very, very useful tool, and our goal is to get you using that tool today. So here is what you get after using Stim. So when you put in the right code, software that defines the circuit that is the surface code for different distances and the error model that you wish to use, you can then plot using the package of tools the logical error rate versus both physical error rate and code distance, and produce something that looks like this. There's a lot of information in here. Two of the most commonly talked about numbers are the error rate at which error correction doesn't help. So at this error rate, the threshold error rate, increasing the resources devoted to error correction, making your code bigger, does not lead to suppression of logical error at all. Useful for theory, but in practice, what you really want to know is something more like this number. At what physical error rate do you get a factor of 10 suppression? For example, in logical error, every time you increase the code distance by 2. So that suppression factor we typically call lambda, and achieving a piece of physical hardware with a good lambda is the primary goal of hardware research in quantum computing. And the goal when using a tool like Stim is to work out what kinds of physical error rates and architectures and error correction codes can ease the burden on the hardware and achieve high lambda with less physical effort. So first, we're going to talk about the syntax of Stim. And just as before, we typically avoid talking about the entirety of the surface code circuit because it's a lot. We are going to focus on just a piece of the surface code, which looks like the repetition code, our tried and true example that we keep coming back to because of its simplicity and being very representative of how the surface code works. This circuit on the right is precisely this cut of qubits out of the surface code. It only focuses on bit flip errors, but it gives you all the flavor of everything that needs to be done. So let's look at the specifics. We want to define this circuit, this repetition code circuit, using the notation of Stim. Fundamentally, the input to Stim is a text file that specifies all of the gates and all of the error processes you wish to be on those gates. And it starts with simply resetting all of the gates. The notation is very compact, so a single R followed by a list of numbers means reset each and every one of those qubits. That is this blue section of the circuit here. Moving on, next, we're going to apply errors. So we have to explicitly list these in Stim. It doesn't assume a particular error model for any gate. If you don't specify errors, the gates are applied perfectly. So we are going to go in and deliberately apply with probability P, 10 to the minus 3 in this case, a bit flip error to each and every one of those qubits. These will be random, independent bit flips. Next, we have some CNOT gates. And again, the notation is compact, a single CX, then a list of gates. This is control 0, target 1, control 2, target 3. That's what you'll see here. Again, we need to go in by hand, add in the errors. First, 2-qubit noise to each of the 2-qubit gates. And we can't forget the extra idle qubit. We apply single qubit noise. The depolarize means an equal chance of every possible error. In the case of a single qubit, equal chance of X, Y, or Z errors. In the case of 2 qubits, equal chance of the 15 possible non-trivial products of I, X, Y, and Z. So IX, IZ, ZY, all of those non-trivial products, equal chance of occurring. And we can keep stepping through it a bit quicker now. These are the CNOT gates pointing up, the single qubit error for the idle, 2-qubit errors for those 2 gates. Another point of note is that when you wish to simulate error-prone measurements, you need to go in and put errors before the measurement gates. After all, once the measurement is complete, there's no quantum anything left. So you have to model an error-prone measurement as an error occurring for the gates, whereas with every other type of error, we model as an error occurring after the gate. So qubits 1 and 3 get a random chance of bit flip before the measurement is then applied. Once again, depolarizing noise for the idle qubits. Now again, we have something new, the concept of a detector. We've talked about detectors extensively through this video series. Now we have their explicit realization in code in Stim. The first part of the notation is an arbitrary coordinate. As the user, you're free to specify this. It makes sense to specify it in some manner that relates to the qubits, so it's easier to remember. It's arbitrary and independent, but it makes sense to do it in a sensible manner. Here we've chosen to represent these detectors as occurring in the coordinates 1, 0, meaning you can think of this as qubit 1, and you can think of this as time step 0, where we're making time steps the number of rounds. These individual measurements are detectors all by themselves, as we discussed in previous lecture. By providing initialized states, we know what this measurement should be. It should be 0, and if it's not, that is a detection event. So the individual measurement is itself a detector. All right, so that's that block of the circuit. One more thing you can do which helps Stim display circuits nicely is you can add tick instructions. So these just divide the circuit up into easy human comprehensible steps that make it easy for Stim to then display it in a neat manner. They don't do anything to a simulation, they just make it easy to check that you've input the correct circuit. We won't keep those just because we don't have enough screen space to do so. Now, let's move on to the next block. So superficially, it's similar. It's a repetition of the first block. It doesn't have the initialization gates. We also want to be able to repeat it multiple times, and we'd certainly not want to have to explicitly write those gates out over and over again. And you don't need to. So Stim has the concept of a repeat block, and there are a few things in here that are new. So this is all common. We're now only resetting 2 of the 5 qubits, all the way down to when we get to here, where we have something new, the shift coords instruction. What this means is that every future detector is going to have its coordinates shifted by whatever is in here. So we're saying shift space, the x coordinate not at all, shift time by an increase of 1. So the future rounds of detectors will differ from the previous rounds by 1 extra unit of time. And again, this is arbitrary. It just makes sense to choose numbers and relationships that are easy to remember and intuitive. Now our detectors have 2 measurements. We're into the regime where to detect an error, you have to compare it with the previous measurement. And here it's good to emphasize that in Stim, the most recent measurement is stored in an array such that you access it by using -1. -1 is the most recent measurement. -2 is the second oldest, and so on. These are further back in time. And in the file, you need to untangle that linear array and work out which measurements you actually need to compare to construct your detectors. Moving on, the last piece of the puzzle is the final round of measurements. This is a much simpler circuit than previously. The key thing that needs to be remembered, however, is that now we need to take pairs of measurements in the final round and compare them with a single measurement in the second last round. So the biggest thing that's new is we now have a detector with 3 measurements in it to form it. Now, one last piece that we need is, well, did our experiment succeed or not? If we initialize our data qubits to all 0s and our experiment succeeds, then we should have the state 0 at the end after all of our corrections, which means any one of these measurements after being corrected should have the value 0. If after corrections these measurements have the value 1, our correction has failed at some point in the time. Our data has not been preserved. That will be recorded as a logical error occurring. Since any one of these tells us that, the observable that we tell Stim to track is any one of those final measurements. We've chosen the -1 measurement, this one, but it would have worked equally well to have chosen the -2 or -3 measurements. They're all final round measurements. They all tell us whether we've successfully preserved state 0 or erroneously been flipped to state 1. All right, now some exercises. So this is where you really want to go, pause the video, download the Stim GitHub repository, go and actually start coding. And the first thing we want to code is just assemble all of the code from these slides into a single file, add tick instructions so it's clear which rounds are groups of gates gathered together, and then modify it. Modify it in a small way just to get a bit of experience with the format. Modify it so that the last round of measurements doesn't occur here later than this round, but actually occurs at the same time, because it could. There's no reason to delay these measurements. Physically, you might as well do them all at the same time. Once you've done that, what Stim really needs is not a single file with a single code distance. You really want to create a Python script that outputs that text file for an arbitrary code distance and an arbitrary error rate p. These should be variables that you input, and the output should be a Stim file with the appropriate generated circuit and error model. If this seems like a lot of work, well, it can be, and there is certainly research ongoing to try to make this easier and more intuitive and not require low-level programming to create the circuits, the detectors, and everything else that goes with it so that you can run a Stim simulation. But for the moment, that's the exercise. Give it a go. Once you've given that a go, the question becomes, well, where does that function go? So here is an example of a similar thing that is already in Stim. So there is a function that you can go and use it to generate repetition code memory experiments. So you might ask, well, why did we do the exercise on the previous slide? And the answer is the built-in functions don't generate an error model identical to what we just did. Built-in functions don't put errors on the idle qubits. So what we've built in the previous slide is an exercise that matches a very common error model in the literature, where every qubit, whether it's either doing a gate or not doing a gate, is subjected to noise. Not the default in Stim. You have to code it. Now you have. So what you want to do is you want to find this function in the Stim Getting Started notebook. You'll find it in section 7, and you want to replace it with the one you've hopefully written. What will happen when you do that is you will be able to generate the output of simulations for various code distances and physical error rates using your function that generates your circuit with your error model. And what you get is something similar to this. For larger distances at low error rates, you will see rapid suppression of error. So let's take things one step further. Keep working through the Getting Started notebook and really take note that when you have bigger codes, you have to have an error rate below threshold to get an improvement. This is common to all forms of quantum error correction. There's always a threshold error rate. The higher that error rate is, the better, the easier it is to build a device that can satisfy that constraint, be less than it, and actually get a benefit from quantum error correction. Similarly, as mentioned earlier, while that's a great number, the threshold error rate, an even better number is the error rate where you get a factor of 10 suppression each time you increase the code distance by 2. Also take the time to find that error rate for both your repetition code that you coded and the service code example in Stim. Once you have those numbers, that gives you the foundation for a great deal of future work. When you want to work out the overhead of an algorithm, you can take the rate of suppression of error with memory and use that to calculate how much error is likely to accumulate in an algorithm throughout its full volume. That will then tell you the strength of error correction you need, the size, the code distance that you will need, and then the overhead of the algorithm. So you can work out exactly how many qubits, how much time is required to execute an algorithm. It all starts with creating plots of this form for simple memory experiments. With that, we're going to close out and say that next time, we're going to take a look at another tool written by Craig Gidney, this time Crumble, and that is for analyzing some of the most complex circuits in the surface code, the ones that actually let you do logical operations and more exotic things such as moving codes around. In this video, we're going to introduce another tool written by Craig Gidney, Crumble. So this is an advanced analysis tool to give you detailed understanding of how Pauli operators propagate through circuits, and in particular, give you insight into the detectors, where they are, what they are. It might seem strange that you would need such a tool, but as we'll see, there are some circuits where it is actually quite complicated to work out what the detectors are in the quantum error correction circuit. And we'll go through, in the very last stages of this video, one of those more advanced examples. So first things first, what is Crumble? So it's a tool that allows you to specify a very general circuit and then put in Pauli operators and see how they propagate. So on the screen, you can see an example of an X error propagating through, in red, a bunch of C0 gates and reaching a bunch of measurements. And what we'll talk about initially is what all that means. What do all these colored lines mean? How is it actually making anything clearer to us whatsoever? So first to recap, when we propagate errors through C0 gates, if there's a bit flip error on the control of the C0 gate, we get 2 bit flip errors at output. In Crumble, these are represented by colored lines. Red for X would then split to 2 red lines out of a C0 gate if it goes in on the control. And similarly for Z, they're represented by blue lines. If it enters the target of a C0 gate, it's going to exit on both the control and the target. If you have an error that goes through a Hadamard gate or some other basis transforming gate, then, for example, you can have an X error, a red line, emerging as a Z error, a blue line. And similarly, there are Y errors, green lines as well, that can occur if you put your errors through an appropriate gate. So those are that's our basis set. Colors: red for X, blue for Z, green for Y errors. Now, meaning. Let's really look at this at a low level and try to work out what it is that the tool is even telling us. So let's imagine you input this circuit into Crumble. And now let's trace some Pauli operators and see what that tells us. Let's in particular look at this Pauli operator. So what is this telling us right now? This circuit prepares the measure qubit in the state 0. The state 0 is the +1 eigenstate of the operator Z. So by putting a little bit of blue right here in the circuit, what we're saying is that at this point in time, in this place in the circuit, we know that we have the +1 eigenstate of Z. That's the 0 state, that's the +1 eigenstate of Z. As we move forward through the C0 gate, what we now know is that at this point in time, we have the +1 eigenstate of ZZ on those 2 qubits. So as an exercise, prove that this is true. It's not a hard proof. Simply start with an arbitrary state that you know is a +1 eigenstate of Z, and then apply the C0 gate and see what new eigenstate you have after doing so. Moving past the next C0 gate gives us yet another Z. And so now we know, because we prepared the measure qubit in the 0 state, that by this point in the circuit, we will have the +1 eigenstate of ZZZ. But now we're going to measure out one of those qubits. So this measurement may return 0, may return 1. It may tell us whether we have the ± 1 eigenstate of Z on this qubit. But since we know that we had just before measurement the +1 eigenstate of ZZZ, knowing after measurement that we have the ± 1 eigenstate of Z just on that middle qubit tells us whether we have the ± 1 eigenstate of ZZ on these 2 afterwards. So these are correlated. The eigenstate of ZZ after measurement will be the same as the eigenstate on the qubit measured. So we have still a known eigenstate up to the result of the measurement. Moving further, there's another reset gate here. This introduces another piece of knowledge to our system. We know, again, that this middle qubit is in the +1 eigenstate of Z. This is an isolated fact, but we can combine it with our knowledge of a known eigenstate of ZZ and say that now we have again a known eigenstate of ZZZ. And that known eigenstate will be whatever this measurement reported earlier. Continuing, after propagating that through this C0 gate, we collapse down to just a Z on this qubit. Continuing, after propagating through this C0 gate, we collapse down to just a Z on this qubit. So what that is saying is that when we run this circuit, in the absence of errors, whatever this measurement reports, ± 1 eigenstate, we'll have that same ± 1 eigenstate here. And since we're talking about single qubits, it means if we measure a 0 here, then in the absence of errors, we'll have a 0 state here, and 1 will imply a 1 state here. So that final measurement should give exactly the same result as this measurement. This is a way to trace operators through a circuit to discover what the detectors are, which set of measurements are detectors. So, what about all of the blue? What does that mean? It means that if any error that anti-commutes with this type of operator, blue means Z, so any X error occurring anywhere on any of these places highlighted in blue, that will lead to a change in whether these measurements are the same or not. So we'll detect it. So this is called the detection region. We have a detector, the set of measurements, a detection region, everything in blue, and then finally a detection event is when you put experimental values into these measurements and you find that the parity is odd. If they don't match, that's a detection event. They should match in the absence of errors. All right, so now let's round this out by actually doing this in practice. Let's fire up Crumble and see how it works interactively. Okay, so this is Crumble. There are several things that you can do in Crumble. You can define the circuits from scratch, or you can simply click on one of these examples, which is what we've done here. We've chosen a surface code example, code distance 3, 2 rounds long. The circuit for that is shown on the right. And as presented, it is perhaps not the most intuitive thing in the world. What we want to do is analyze that circuit using Stim to work out where the detectors are in exactly the same manner that we did by hand the simple example on the slides. So let's do that. Let's choose a reset gate. Let's put a Z operator on it. You do so by pressing Z1. The number is just a label. There are many labels you can apply. The operator is our Pauly Z. So we've put a Z operator with label 1 on that reset gate. And what you can see on the window on the right is that operator propagated through the circuit. And again, at any slice in time, what all of this blue means is that because we initialize this qubit to the state 0, we therefore know the eigenstate of Z operators touching all the blue locations at that point in time. Let's go all the way up to the next measurement. And as before in the slides, we're going to click on that measurement. We're going to include it in our set of knowledge. We're chopping that qubit out of the operator. So now, based on the knowledge of the result of this measurement, we will know what eigenstate we have on this 4-body operator. Z, 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 Z on these 4 qubits. And that is indeed what you see over here as well. So the measurement and reset have worked together to prepare a known eigenstate of the stabilizer Z, 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 Z on these 4 data qubits. We're not done yet. We haven't found the detector. We keep going. In the next round, there's another reset. As before, we want to include that in the process. And you might say, well, how did we know to include that? And the answer is we don't. Sometimes it requires a bit of experimentation as to which resets, which measurements to include to extract useful information. You know you've extracted useful information when all of these lines on the screen form a closed region. And we can do that by putting the final Z operator here on the final measurement. And now look what we have. We have a nice closed region. We have a detection region, which includes 2 measurements, and those measurements form a detector. Now, you could argue that this is perhaps not the most complicated example. This is the standard surface code. It does the same thing over and over again. So we kind of knew that if we chose a sequence of resets and measurements all in one line, we would get a detector, and we probably could have done that without any advanced tools. But let's take a look at something a bit more complicated. This is a circuit that's used as just one part of the process of measuring a logical qubit in the Y basis. It's not the complete circuit, just a small, complicated piece of that procedure. And there are parts of this circuit, for example, over in the corner, that are extremely similar to just the regular surface code. For example, if I choose this reset here and I propagate it forward, focusing on just these qubits, L key limits it to just those qubits, you'll see something extremely similar to what we had in that that part of the circuit prepares an eigenstate of the 4-body Z stabilizer around here. But that's not true everywhere. If we go to a more complicated part of the circuit, for example, if we zoom in on this region and we do that same thing here, put a Z operator on there, what you'll see is that you get a big mess. It does not lead to a state that can be measured easily. These purple highlighted minus signs tell you that this measurement will give you random, useless information. Okay, so this on its own is not going to lead to a detector. It will just lead to random numbers. And so what you can do with this tool is you can play around and ask questions. Well, maybe I need to include this reset as well. And you can ask yourself, does that work? And the answer is no. Still have a measurement that's going to lead to a random number. So you can come back and you can erase that and try a different one. Say, well, what if we include this reset? And you have a look at it and you say, right, now I have information that is not going to lead to random measurements. Indeed, I can go to this measurement here and put an X operator on it because it's red. And this measurement here, put an X operator on it because it's red. And this measurement here, because it's blue, we'll put a Z operator on it. And now what I've found is the combination of these two resets in the beginning, these two resets, and these three measurements are all required just to work out a known eigenstate of the usual surface code operator, the stabilizer ZZZZ. And that's the power of Crumble, allowing you to find these complicated structures that you may not otherwise be able to find, and build some intuition as to how you actually build detectors. As one more example, this showed us starting from resets and finishing with measurements, with the output being a known stabilizer value here. Well, let's, instead of just starting with the state on resets, let's start with that known stabilizer and see what this circuit does to it. We clear everything. We start with the known stabilizer from a previous round. Imagine a previous round prepared a known eigenstate of this stabilizer. And now we want to know, how does this circuit measure that? Well, again, we can put the Z on here. We can go through the final round, and we can see that these two measurements here, right, this one in the Z basis and this one in the X basis, these are what are required to know what eigenstate of the four-body ZZ stabilizer was. So we can use those two measurements to compare with whatever prepared the known eigenstate in the previous round to form a detector. So we've gone through two things just now, starting with resets only and seeing what measurements need to be combined with those resets to prepare a known eigenstate of a stabilizer, and then also started with a known eigenstabilizer and seeing which resets and measurements need to be coupled together to measure that. And these are sort of two halves of the puzzle. Though that information in two separate rounds allows you to form detectors even in very complex circuits of this nature. And that brings us to the end of the course. We've covered a lot of ground. We started off with quantum computer architectures, and then we worked through quantum circuits all the way through the types of errors they can suffer, stabilizers, quantum error correction circuits that detect errors, repetition code, the surface code, how to simulate that in Stim, and finishing today with Crumble, how you find detectors in complex quantum error correction circuits. This is, of course, not the end of the journey. There are many exercises that come with this course. I hope you enjoy working through those. Also, there's much further reading. There's a world of further reading in the lattice surgery aspect, taking you through how you do computation in the surface code, and more advanced aspects with regards to Crumble and advanced logic gates, the single qubit gates S, the Y-basis measurements that I hope you get your teeth into and explore further as well. On that note, it's been a pleasure presenting. I'm Austin Fowler. Thanks for your attention.